Okay, so this part is part 4, and we're going to be using part 2's equation, which is the time-varied equation of t at some time later at spatial arrangement j is equal to t at an earlier time j plus r multiplied by n j at a spatial arrangement to the right minus 2 t n j plus t n to the left. Alright, so what's important about this equation is that we know from the first part of this series that we use the equation of e to the I k change of x multiplied by e to the k squared change of x negative alpha k squared t. Yeah. We know that that goes in and solves for the diffusion equation. So, consequently, we can say that equals that. And the nice thing is that we just start plugging that right back into there with the constraints of the spatial arrangements and time being relatively the same for each one of the increments. So we can plug that in and solve it out for it. So we get t n plus 1 j is equal to t n j, right? We can take out tj, t and j from each one of them and say it's plus 1 multiplied by r. I'm going to take that out here too, so it'll transfer through all of it. Now what's plus 1? That's just going to be the first one, right? The one to the right of it. I k change of x, and then minus 2, that's going to be the one in the middle, minus 2, and then plus e to the I k change of x. Okay. There we go. Now that everything's substituted back in, we can just simplify for things. So, nice thing is that we know from a law, identity law, when you add those two things together, it equals cosine. I just realized this is negative because it's 1 to the spatial discretization to the left of the temperature that we solved before. So what's negative? When you add those two together, it equals cosine. But when you add two i's together, it makes it negative 1. But since it's starting negative, it cancels out, so it's just regular cosine. So 2 cosine, right? So t n plus 1 at some spatial arrangement or discretization. T n j 1 plus, we can factor out 2 because, right, this would be 2 cosine k change of x minus 2. So we factor that out. We get 2 cosine k change of x minus 1. It's actually very fast. Now, the important thing is that we have to figure out, well, what can 2 be in order to keep the constraints for the stability, or what can R be? So we don't have to worry about this section anymore. We just have to worry about this part right here. So that's the -1. 1 plus 2r. Oh, an important thing to note here too is what is the maximum cosine can be? Maximum it can be in this case is -1. Yes, in any case actually. So maximum it can be is -1, so it's going to be -2 on the inside there. Alright. Less than 1. We subtract 1 from both sides. We get 0 and -2, right? So now we got -4, -2, subtract -4 from this side over here, and since we're subtracting by a negative, it flips it, so it's 1/2 greater than r. So r has to be less than 1/2 for the constraint for stability. So that is part 4 for the von Neumann stability analysis for the second equation, or the part 2 equation.